Hi everyone, my name is Bing Zhuo, a PhD candidate from Technical University of Munich. Today I'm going to introduce a direct data-driven approach for synthesizing safety controllers for uncertain linear systems. This is a joint work with Professor Maziz Zamani from CU Boulder and Professor Marco Kakama from Technical University of Munich. Nowadays, ensuring the safety of control system has received significant attention due to the increasing number of safety-critical real-life applications, such as autonomous vehicles, smart power networks, and so on. Note that there are lots of model-based approach for synthesizing safety controller over this system, but sometimes it will be challenging to apply these methods. First, obtaining an accurate model requires a significant amount of effort, and even when you are able to obtain a model, the model may be too complex to be of any use. If you are trying to identify the system, the identification approaches you use could be complicated, time-consuming, and expensive. Therefore, here we are considering how to synthesize safety controller directly based on data. Here's the formal formulation of the problem we're focusing on. We focus on uncertain linear control system like this, with disturbance belong to an unknown but bounded disturbance set. Here, unknown but bounded disturbance set means that all the disturbance belong to a bounded set and the bound is known. However, we do not know what is the distribution of the disturbances. Additionally, we consider state constraint and input constraint of the form for polytope, and we consider how to synthesize a state feedback controller directly from a single input state trajectory, such that both the state and input constraint are respected. So here directly, I mean, I want to use direct data-driven approach with which I directly map data into controller parameters without any intermediate identification frame. So you may ask, why not? You have a linear system, you have data. Why don't we first identify matrix A and B and then apply those model-based approach? Here, I want to motivate the application of direct data-driven approach by the following example. Here, we focus on a system with 4-dimensional state set and 1-dimensional input set. But the disturbances follow an asymmetric distribution. We try to use ordinary least square to identify the matrix A and B, and here are the results. So the blue line in each subfigures denote the real value of those matrices, and the red line denotes the evolution of the identification result with respect to the number of data and that is employed in the system identification process. So you can see that actually the identification results does not converge to the real value. As a key insight, system identification using ordinary least squares requires disturbances subject to symmetric distribution with expectation 0, so that when you connect more and more data, the disturbances will cancel out with each other so that you converge to real value. But it doesn't work when the disturbances are not symmetric. And typically, they will assume that the disturbances are subject to Gaussian or sub-Gaussian distribution. And here, we do not need this assumption. We only need to know the bound of the disturbances so that our approach can be applied even when the disturbances follow an asymmetric distribution. In fact, we do not have any assumption on the distribution of the disturbances. So I will come back to this point when I introduce the case study. Here's the overview of the direct data-driven approach. We have a desired specification. We have a data set connected from the underlying system. We pass them to the data-driven computation process, which include data pre-processing and actual data-driven synthesis. I want to emphasize that the data needed for the data-driven computation is only a single trajectory connected from the plan, which is quite efficient. First, I want to provide you with the high-level idea regarding how do I enforce safety. Concretely, we are trying to use data to find a gamma ISI set for the underlying system. So here's the properties of the gamma ISI set. Consider the state constraint. The gamma ISI set is an ellipsoid contained within the state constraint, so that for all states within the gamma ISI set, there is a common state feedback controller that can drive the system within a smaller ellipsoid, which is the blue one, when there's no disturbances adding on the system state. Then, if the distance between the blue ellipsoid and the gamma ISI set is bigger than square root of gamma, so the gamma is the bound of the disturbances, then we are able to ensure that whenever the system starts within the gamma ISI set, we are able to keep the system staying with the gamma ISI set at the next time instant. And considering that the gamma ISI set is within the state constraint, we are able to enforce the safety property. So here is the formal definition of the gamma ISI set, which is an ellipsoid, as I have mentioned. So we connect data offline from the system, and we organize the data like this. So x0n is the sequence of state, and u0n is the sequence of input. And we construct x1n by shift the x0n by one time instant. We require that the data we connected fulfill the condition of persistency of excitation, which means that the rank of the matrix here should be equals to n plus m, in which n is the dimension of the state set and m is the dimension of the input set. If you have data that fulfill the PE condition, you are able to ensure that the data in hand encodes sufficient information about the underlying system dynamics so that you can synthesize something, which is the gamma ISI set, that's valid for the system only using data, even though you do not know the underlying A and B. So this is the key insight. Here's the main implementation of our proposed approach. We are trying to obtain the gamma ISI set along with the controller by solving this optimization. We construct the first constraint by selecting a kappa within 0 and 1, computing the C accordingly, and write it down. So Q is the decision variable for the optimization process, optimization problem. So as a key insight, the kappa here denotes the deflation parameter of the blue ellipsoid with respect to the green one. So there should be a real number between 0 and 1. The second condition contains the data we have connected. Concretely, we construct N1 by kappa, Q, and Z bar. So Q and Z bar are decision variables for the optimization problem, and N2 contains the data we have connected. The third and the fourth constraint corresponding to the safety set and input set that we want to enforce. And the last line contains some slack variables for solving the optimization problem. Here, we are trying to maximize the volume of the gamma ISI set such that all these constraints are fulfilled. When you are able to obtain a solution by solving this optimization problem, then one can construct the gamma ISI set and the controller in this way using Z bar and Q. To summarize, we have a data set. We select data from the data set. So here I denotes the number of data sequence that has been passed to the solve the optimization problem I've mentioned in the previous slide. We check the selected data to see whether it fulfills the PE condition. If no, we select again. If yes, then we set the initial value for kappa and try to solve the optimization problem. If you're not able to obtain an answer, then you select a new kappa in a bisection manner. So here, E is the precision parameter for the bisection. If this E is respected, then we pass the new kappa to solve the optimization problem again. Otherwise, we increase I by 1 and check whether I exceed the maximum number of data sequence that can be passed to solve the optimization problem. So this Imax is selected by the user. So if Imax is respected, then we select data again and rerun the whole procedure again. So the procedure here either end with successfully solving the optimization problem here so that you obtain a gamma ISI set as well as an RSI-based controller, or it ends inconclusively. So in the case study, we focus on an linearized inverted pendulum. So the underlying model for connecting data and simulation is like this, with disturbances belong to an unknown but bounded disturbance set. So the bound is related to the time interval. Here we generate the disturbances following an asymmetric distribution to show that our approach also works even when the distribution of the disturbances are asymmetric. So I want to emphasize that the system model and the distribution for the disturbances here are only used for connecting data and simulation. So we do not need to use the information here for synthesizing the gamma ISI set in the controller. So all we need is data. The model for the inverted pendulum has a 4-dimensional state set. So including the state includes the position of the card, the velocity of the card, the angular position of the pendulum with respect to an upward vertical axis, and the angular velocity of the pendulum. So here we use the acceleration of the car as the input of the system, and we want to restrict the input within -5 to 5. Additionally, we also define a safety set over x1 and x3. To synthesize the gamma ISI set, we connect data with length 107. We obtain the database gamma ISI set like this with the state feedback controller here. So this is the feedback gain. We simulate the system by randomly select 100 initial state from the gamma ISI set and simulate the system over time horizon to 100. And here's the result. We can see that both the state set and the input set are respected. To summarize, in this paper, we focus on synthesizing controllers over uncertain linear system directly from data so that we do not need to perform any identification processes. Particularly, we only need a single trajectory connected from the underlying system, and the trajectory should fulfill the condition of persistency of excitation. If you are able to obtain a controller and the corresponding gamma ISI set, you are able to enforce the desired safety property over infinite time horizon. In the future, we are going to extend the current results to uncertain polynomial system, and we are also interested in investigating on direct data-driven approach for synthesizing control barrier function instead of gamma ISI set, because we realize that the gamma ISI set is actually a special case for the control barrier function. This brings to the end of our talk today. Thank you for your attention. If you have any question, feel free to contact me through email here. And you can also access the archive version with proof of my paper using this link or simply scanning this QR code. Thank you.